Okay, welcome to this Introduction to Semiconductor Devices Problem Solving Session hosted by NPTEL. The course code is NOC 23E82. Today is September 16, week 8 for this session. My name is Amit. I'm a PhD scholar at ISC Bangalore. What we have been going through the in the previous sessions, we first saw that we can classify materials in terms of their electrical conductivity, and so we saw insulators, metals, and semiconductors. And peculiar property of semiconductors is the what we were interested in. Then we went into a bit of quantum mechanics using the de Broglie wavelength lambda equal to h over p, then Heisenberg uncertainty principle. Finally, we saw something called quantum well. So it looks something like this. You draw the potential on the y-axis, position on the x-axis, and this is the well. So essentially, this is an infinite well. This means this level is infinity on both sides, and if it's only on one side, this is asymmetric well. So what we saw is that if a particle is inside, it cannot escape, and its energy is quantized by the virtue of being stuck in this well because it cannot escape. We also saw it was asymmetric. That means it can be, so this is asymmetric quantum well. Symmetric will be, let's say, from minus L to L. And one of the most peculiar things we saw in quantum world was this, that let's say again y-axis is your potential and x-axis is your position, and let's say this is some potential barrier of v naught, and if a particle is coming with some energy E, we know classically this particle cannot cross this barrier. It can never have this energy. So this particle will never be found on, let's say, this position x1, but we saw that it can tunnel through this barrier. There's some finite probability. This phenomena we refer to as quantum tunneling, which we see over here. This is peculiar to quantum world. This we do not observe in the classical mechanics, so to speak. Then we combined all these principles of quantum mechanics. We saw that how the two atoms can come close together, and with, let's say, Avogadro's constant number of atoms 16 to 10 to 23, they come close together. Their orbitals overlap, and all those things happen. And we applied the Ronick-Penny model and the you say that thing, I'm forgetting, the periodic potential, and we solved it essentially. That we simplified, made it a model, and then we solved, and we introduced something called dispersion relation, which is the energy and wave vector diagram, E versus K. K is your 2 pi by lambda. Lambda is your wavelength. How does the wavelength come into picture? Remember, de Broglie wavelength is nothing but h over p. P is your momentum, h is your Planck's constant. And we saw that indeed when you do all this quantum mechanical apply all these quantum mechanical principles, what we could see is that in some materials we can see that, so this band is filled and the electrons can reside above EC, this is the conduction band, below EV, which is the valence band, this is the forbidden gap. I'm drawing it flat. It was actually not flat, it had curvature. EC actually had curvature when you draw EC versus K. Okay, and this curvature determined what is known as the effective mass. The good thing about effective mass is all the quantum mechanical effect, actually I should not say all, but all the effects that we usually encounter in our electronics, semiconductor electronics, can be contained just in this entity called effective mass, usually denoted by m star or m effective. So it can be different for electron and holes, right? And then we saw that in a semiconductor, let's say, which is made up of silicon, we can dope. So some of usually there are 10 to the power 22, 10 to the power 23 atoms, right? In a piece of material, let's say, then you can dope it 10 to the power 16 cm minus 3 and so on. Okay, and if you dope it n type, that means you are making it so that there are more number of electrons, right? By doping, let's say, phosphorus or nitrogen, or acceptor atoms, like you can dope it with boron, okay, then to make it p type. Closely linked to that, we drew Fermi levels. So for a p type semiconductor, we saw something like this. So it was EF, the Fermi level. The Fermi level is actually the level at which the probability of finding an electron is half. So again, this Fermi function is has basis in quantum mechanics, but and its position in the band gap we saw was depending on the doping. So if the doping is p type, we saw it was closer to valence band. If it's n type, it's closer to, so this is for n type, the green is for n type, right? And then again from this, again from Fermi function and all that, we saw there's some carrier concentration at equilibrium. So this Ni denoted that intrinsic carrier concentration for electrons. If you recall, it's 1.5 10 to the power 10 cm minus 3. Nc and Nv were some constants which, when we solved those quantum mechanical expressions, and we had um, some assumptions that for a non-degenerate semiconductor, which you can see over here, non-degenerate semiconductor is what? When EF minus EC, its magnitude, just check the sign, should be greater than equal to 3 kd, and consequently for y it can be EC or EV. If this gap is more than 3 kd, this means doping is not very high, the semiconductor is non-degenerate, and all the analysis is usually valid. And we also saw the carrier concentration depends on temperature. For instance, a very low temperature at 5 Kelvin, 10 Kelvin, none of the dopants that you have put here, N type or P type, will not contribute. Their bonds, their electrons will still be attached to their nuclei. Okay, so they cannot contribute to electron concentration. Extrinsic regime is the regime the temperature is high enough, usually 100 Kelvin, 200 Kelvin, that all of them have donated their electrons, and thus they can contribute to current. Intrinsic is when you raise the temperature so high that the intrinsic bonds of, let's say, silicon, the background semiconductor, they start to generate electron hole pairs, and the concentration rises dramatically. We usually want to operate in the extrinsic regime, right? Okay, but as I told you, the uniform need not always be constant. So you can have non-uniform doping, you can have linear doping, exponential doping, and we saw that the conduction valence band will no more remain flat. Which means is that, so conduction valence band is essentially what we mean by them is just, this is just potential, right? This is potential energy. Potential energy as a function of distance. So you can see dV over dx has a slope. dV over dx is nothing but your electric field. If you recall, is minus grad V, right? Slope of potential. So when you have non-flat bands, you have a built-in electric field, and you can take it vice versa. So if a sloping potential, this means a field will usually mean sloping potential. And if there's a field, usually this term we introduce called mobility, which has something called Vd equal to mu E. So Vd is your drift velocity, mu is your mobility, E was your electric field which the carrier is facing, and this was drifting. So if you apply electric field, F equal to Q times E, you put F equal to effective mass times acceleration, you can solve that. Conductivity you saw as Ne nu, for instance, for electrons you can say Pe mu P for holes, right? And conductivity you can, from the Ohm's law, we saw how we did. This is another way which carriers can get transported, that's by diffusion. Let's say you have 10 to the power 20 cm minus 3 of electrons in one corner, and on the other corner, on the other side of the semiconductor, you have, let's say, 10 to the power 15 cm minus 3. There's a huge gradient, so the electrons from higher concentration will move to the lower concentration, which we call the diffusion. And the diffusion constant and the drift, the mobility, sorry, here are linked by something called an Einstein relation, and with the Boltzmann constant and temperature. All of this analysis was only up to at equilibrium, this at thermal equilibrium. What if we disturb the equilibrium, let's say by shining some light or injecting some currents? So we saw that, or and which was determined by something called a minority carrier diffusion equation. By the way, all of this is in the videos, the link for which I have shared of my YouTube channel. If you're interested, you can go through that. We saw that how the excess of minority charge carriers are related to drift, which we saw here, diffusion, which we again saw. Generation recombination means you're generating due to some light or injecting. Recombination means when there's a large amount of electrons and holes in close vicinity, some of them will recombine, right? So that's what we talked about. Finally, with we are equipped with all the understanding of the concentration of electrons and holes, as well as their transport mechanism, primarily drift and diffusion, right? And then we applied this understanding to something called a very simple device called a p-n junction. It means you take a p-type semiconductor, you take an n-type semiconductor, you bring them close together, and let's see what happens. So here on the left side you have large number of holes, right side you have fewer number of holes, so holes will diffuse, and in turn they'll leave behind their lattice ions, the dopant ions. Okay, so we saw different flavors of p-n junction, like step p-n junction means one is p, one is n. Other can be linear p-n junction, means the concentration of holes is gradually decreasing, 15, 14, 13, and so on, right? And pin junction is where you have p junction, you have an intrinsic region, means no doping, and an n junction, this is called pin junction. Pn plus means you have moderate doping on p side and high doping on n side. Moderate, let's say 10 to the power 15 to 10 to the power 16 cm minus 3. High means, let's say, 10 to the power 18 cm minus 3. So there's a huge jump. I mean, these values have an order of magnitude difference or more. Then we saw a very because this is still a complex problem to solve. In order to solve, we made some assumption, which we refer to which we call the depletion approximation, which is which provides us a solution to the Poisson's equations, and we saw the depletion region forming and so on. And these terms is the key takeaway, that the depletion rate, peak electric field, stored charge, built-in potential. We have been referring to these terms in each and in every class, and same will be true for today as well. All right. Now and finally we saw, when we are under non-equilibrium, we introduce something called a quasi-Fermi level. Means, let's say on the p side and n side you have different. So this is the p side, so we have introduce a Fermi level called EFP, and on the n side we introduce a Fermi level called EFN, right? And then we saw in forward bias you can inject some carriers, the potential barriers. So PN junction, by the way, under equilibrium looks something like this. This region you see is the depletion region, where the bends are bending, the EC and EV are bending. If you apply some external bias, positive bias, this means P is connected to P side, sorry, positive side of the battery, then you can inject some carriers. This barrier will get lowered, and the diffusion of, for instance, holes in this case can come to this side. They'll recombine with electrons here, and this current can flow. The reverse bias, opposite will be true. So this region will be widened, and there will be no transport of electrons. However, if some charge carriers are somehow enter near the periphery of this depletion region, they will be swept away by the high electric field. And corresponding things, because what you can clearly see here is that there is a charge that is there. So for instance, on this side you have negative charge, on the P side, on this side you have positive charge. So essentially you have a charge in there, and whenever charge is separated by some distance, an entry called capacitance kicks in. So that's what we saw, the junction capacitance. Finally we saw second flavor of devices, which is called the metal semiconductor junction, wherein we saw that on the one side it's metal, so this is your metal, this side it's semiconductor. So we saw this is also known as, by the way, Schottky junction, and the bends are one bending based on the work function. The work function is your distance between your Fermi level and the some vacuum level. Okay, and this depletion width again comes into the picture. The current in Schottky junction we saw was determined by thermionic emission, and the reverse saturation current, similar thing like a PN junction, but this time it's different. The temperature dependent or different. Richardson constant comes into the picture, which is the one of the key difference. That's what I mean to say. And the Schottky context can be of two flavors depending on how the bends are bending, rectifying and ohmic. Finally, we come to the at least which some people call the hero of the course, is the MOSCAP, metal-oxide-semiconductor capacitors. We saw the different regimes: Fadman, accumulation, depletion, and inversion. We'll again go through them in a bit. And we saw what do we mean by strong inversion, and how do the electric field and potential profiles look in a MOSCAP, an ideal MOSCAP, that is. The key terms which came last time was surface potential and the voltage drop across the oxide. And we, in the towards the end of last class, we saw also a peculiar device called semiconductor oxide semiconductor capacitor. So that was a different thing. All right, so let's just quickly just revise about the MOSCAP. So you have a MOSCAP on the left. Name explains: metal, oxide, and semiconductor. So what do you mean by ideal MOSCAP? The metal semiconductor Fermi levels are the same, and usually there are no traps in the semiconductor oxide interface or in the oxide as well. And the metal is equipotential, and semiconductor thickness is large, which is usually the case, and oxide is a perfect insulator. So the first, second, and the last ones are the assumptions that are the violated the most. Okay, in fact, first and second are the violations that you'll see. Are the assumptions that you'll see violated the most. Okay, and we'll violate some of them today. Okay, and as far as operation is concerned, when low bias is applied, so you can see low bias is applied and Fermi level is same throughout. So actually the Fermi level is not drawn here for your on the metal side, but please remember they are the same. So EF, you can see the metal here as well, EFM, let's say. So Fermi levels are same, no electrons will transport to either side, so bands will remain flat. However, if you apply slight negative voltage, so remember this is a p-type semiconductor that you are seeing here, because EF is closer to EV. This is EV rather than EI. So a p-type semiconductor, if you are applying a negative bias, what you are doing essentially, the excess holes will get attracted to this interface now. To this interface. So this interface will become positive charge, right? What's happening is holes are getting accumulated. You can see that at the interface, EF and EV are coming closer as compared to the bulk. So if you recall, the concentration is directly proportional to EF minus EV over KT. So if you reduce the gap, the concentration of holes will rise exponentially. Finally, the reverse will happen if you apply positive bias. The holes will get repelled away and you will see a depletion region forming. Negative ions will be exposed, which are the acceptors in this case. These are the acceptor ions, the dopants that you had put. However, and you can clearly see that in this case, the EI at the interface, at the oxide semiconductor junction, is actually equal to EF in the bulk. So what's happening is that, and when you have applied such a VG, then this device at the interface is no more p-type. It's actually intrinsic. What happens if you apply even a larger positive bias? You can see the EF has now risen above EI. So in the bulk it's p-type. However, at the interface, just look at this region, it's n-type. The nature of semiconductor has changed just by application of one bias. This is what we call inversion. Okay, now we'll get into the problems. Just to this is a problem just to summarize, just to wake all of us up that what we have been talking about. So the question says, consider the steady state charge distributions in an ideal MOSCAP. So remember, I had been talking about that. Always ask yourself whether the capacitor we are talking is ideal or not. The question itself says that. And then the various biasing conditions are shown in the figure, which you don't know yet. But 1 stands for accumulation, 2 for depletion, and 3 for inversion. So for instance, let's say, what is this? Let's just try to identify this. So you can see on this side of the semiconductor we have a negative charge, because so these are charge profiles. So this is a negative charge, this is a positive charge, and you can clearly see there is no depletion that is happening. Depletion is denoted by this gray color. So no depletion is happening here, right? So this is accumulation. Because remember the 4 regimes, flat band, this is not flat band because we can clearly see some charge. There is no depletion, and if depletion is not there, inversion cannot be there. So this has to be accumulation. Let's look at this fellow. So again, this is a negative charge here and a positive charge here, and this is a positive depletion charge as well. Okay, so what's happening here is that something must have happened. It must have depleted semiconductor and then inverted it. Then only you will get this sheet charge at the oxide semiconductor interface. This is clearly inversion. What about this? So here we have a positive charge on the metal side, and you can clearly see a negative depletion charge, right? And also electrons are being accumulated here. This blue sheet that you see, this is again at the interface, hence we know this is inversion. So again, you see a depletion charge and also an inversion charge. So this MOSCAP is also under inversion. Let's look at the last case. So you have a positive charge on the metal plate. What's happening in semiconductor? It's depleted, but it's not inverted because you don't see any sheet charge on the oxide semiconductor interface. So this is under depletion. There is no flat band diagram. A flat band will not have any charge anywhere. Okay, so we identified the regimes, but we are also required to identify the semiconductor. Okay, so let's look at this. So what's happening is that this is accumulation. Accumulation will always happen of the majority charge carrier. So this is a p-type. Why do I say p-type? If it's p-type, it will have majority holes. So if you apply a negative charge on the metal, what's going to happen? A positive charge, which is majority here, the holes will get accumulated on the oxide semiconductor interface, right? So we know that first one, this first charge plot here, the diagram here, corresponds to p-type, and accumulation stands for number 1. So first p1, so this is true. No, this cannot be true, so this option is wrong. This option does not talk about it, so this is correct. Oh sorry, this may be correct. 1p1 is what I'm looking at. This is also correct. Yeah, so this is wrong definitely, and this is wrong. Let's look at the other options. So here you have applied a negative gate bias, right? And you can see that it has depleted. Depleted by a depletion charge is positive. When is a depletion charge positive? When you have donors, when it's n-type. So remember, N type, you, let's say for a silicon, you dope it with sorry, with phosphorus, let's say. So phosphorus will donate an electron and itself will become positive charge. That is the depletion charge. It cannot move around freely. That's the depletion charge of the dopant that you see here. That happens in case of N type, right? And you can also understand it this way: if you apply negative potential on the gate, on the metal here, what's it's going to happen is going to repel away all the majority charge carriers, the N type, right? And positive charge core or lattice atoms will be exposed. However, if you apply an even great negative bias, the n-type semiconductor will become inverted, and you will see a hole of minority charge, which is holes, get accumulated on the get collected on the oxide semiconductor interface. This also tells us this is n-type. In inversion, so second figure corresponds to n-type. This is incorrect. And inversion is denoted by 3. This is also incorrect. This is correct. So this is incorrect, this is incorrect. Actually, this is the correct option. Let's just go through the third one. Third one, I am applying a positive bias, and you can see we have some negative depletion charge. When is the depletion charge negative? When we have a p-type semiconductor. So for p-type, let's say you are doping the silicon with boron. So boron will accept an electron, will become a p-type, right? So when it becomes a p-type, so it will that's what you see, this negative, the boron ion. Alternatively, you can say that since it's holes is its whole majority, so when you apply positive bias, the holes will get repelled, you'll get a negative depletion region. And then finally, if you apply large enough positive bias, the semiconductor, p-type semiconductor, will get inverted, and you will get electrons at the oxide semiconductor interface. This also dictates third corresponds to p, third is p, and it's in inversion, denoted by this number 3. Finally, fourth is very similar to this, except that 3 and 4 are exactly the same, except that fourth has not gone into inversion yet. It's only a depletion. Okay, so we denote like this. Okay, this is why I'm revising this, because in the last class, if you recall, in the last session, I told you just ask yourself 3 questions. Are we talking about an ideal MOSCAP? Second, is it N MOSCAP or P MOSCAP? And thirdly, what regime is it in? Regime we have seen whether it's flat band, accumulation, depletion, or inversion. So this is just a problem to warm you up. All right. So I'll take a pause here, and if there are any comments or questions, just feel free to ask. In fact, at any point of time, you can stop me. Sometimes I tend to go fast, and sometimes I tend to go very slow. If you have like any comments, just please stop me there and then. All right. Okay, I'll assume that why I keep repeating this problem again and again, because this is actually the very fundamental of what we'll see the next device, hopefully MOSFET. So unless and until you have MOSCAP at your tips, right now we are applying potential only to, remember, only one terminal, then the metal terminal here. In MOSFET, you'll have 3 terminals at the very least, 4 in some problems. Actually, there are always 4, but we reduce it to 3 terminal problem. Here you have one terminal. If you have difficulty in understanding the one terminal problem, it will become much more difficult when we have 2 more terminals added, right? So that's why just take your time with this, ask questions in the forum, or discuss with your friends, your professors, and whatnot, right? But just make sure that you feel comfortable with this, with these charge diagrams, electric field profiles, and all, so on and so forth. Okay, so moving on, what we have is a fairly straightforward question here. In the MOS capacitor, the capacitance at the threshold voltage is T2. So we had discussed this term, threshold voltage. So this is the voltage we defined at which we say that strong inversion has started. So we'll see what do we mean by that. And again, when we talk about nothing is given, I'll assume it's an ideal MOS capacitor. Okay. So first we need to understand how the MOS capacitor can be modeled. So you have it on your screens. So on the right, we just discussed it in the last problem. So I'm here talking about a PMOS cap. sorry, an NMOS cap, an NMOS. All right, let's check if this NMOS. So if I apply negative potential, right? So NMOS means it's P type. The substrate, the semiconductor is P type. So if I apply negative potential at the metal, so left is your metal, this is your oxide, this is your semiconductor. So if I apply a negative potential on the metal, so it will, so here it's P type. There are a lot of holes here. They'll get attracted to this interface. They cannot pass the oxide. Remember, it's a perfect oxide. It's insulator. They can only come up to here, and you can see they are accumulating here. So this is an NMOS in accumulation. In depletion, we saw that we apply a positive bias, the holes will get repelled, you will get a depletion region. If you apply an even higher gate bias, then the depletion region will not extend. Rather, at the surface, what you will see is a collection of the electron. The sheet charge of the electrons is denoted in green here. Can you see this? Na is another hint to tell you that what we are talking about here is indeed a P-type semiconductor. The substrate, that is. It gets inverted, that's a separate story. But inherently, it's a P-type semiconductor. And if you want to denote the same thing, the charge story here in terms of potential. So here we have phi s. We saw in the last class is something called the surface potential. Okay, which we defined it as the EI at surface. Okay, this interface is sometimes referred to as surface. Please note that this is the, when I say surface, I mean this, not this. Okay, please just be careful. This is the surface. Metal oxide interface is what I'm calling the surface. EI surface minus EI bulk. This is the definition. Okay, so if we see that at 0, this means nothing is happening, right? And if EI surface is higher than your EI bulk, right, this means you're turning more and more towards the depletion regime, and finally inversion. So 2 phi f is somewhat rather at this point of time we say strong inversion has set in. So what's happening? Let's just look at this charge diagram. So at the threshold voltage, which is closely linked to this fellow at the strong inversion, so what we are seeing here is that this charge on the metal side is counterbalanced by two charges. First is blue is balanced by green. So sum of the part in blue. Remember, it has to be neutral overall. It's in steady state, that is. So Q has to be balanced by this negative sheet of negative sheet, which let's say I'm calling it as Qn. So magnitude of Q has to be equal to magnitude of Qn plus this block here, right, which I'm writing it as Na times xd. The units are coulombs per centimeter square. Remember, this is cm minus 3, you multiply it by centimeter. So coulombs per centimeter square. This is how the charge balance equation will look like for inversion, that is for this part. Okay, so what I'm seeing is that this, now think in terms of capacitances. This means there's an oxide here, right? So oxide has this on one plate and this on the other plate, correct? So what we do it is that we say that these are two capacitances, and remember this is also negative charge that we have throughout here spread out. This is also behaving like a capacitance. So anything which is storing charge, so to speak, we are modeling it as capacitance, right? But one of our terminals is here. So if you actually look at the, this is your metal, this is your oxide, and this will be your semiconductor. Metal oxide semiconductor. So what I am doing is that I am applying some positive bias to metal. VG, we call it VG, and the source is, let's say, grounded or to the negative terminal. So what's happening is that essentially, so you're applying this. So just think of it. So circuit has to be complete. So this is something like this. It's connected to positive terminal, and this is connected to the negative terminal. So this is the complete picture actually. You can see that these are in series. This capacitance, the oxide capacitance, and the depletion capacitance. This is capacitance rising to the depletion. Call it the depletion capacitance. You can see this and this are in series. The oxide capacitance is in series with the depletion capacitance, and thus we'll see that this is the option. Oxide capacitance in series with depletion capacitance. Actually, you can argue that this is true even when we are not in inversion. You can even argue that, but then some terms will drop out. That's the only difference. Okay, the truer term is this charge balance expression. Okay, and the electric field profiles, if you recall, that we did in the last class. Capacitance modeling is just for our easier understanding, because resistances and capacitances is something that at least we have seen. By seen, I mean you have solved problems with it maybe in your senior secondary, or if you are in first or second year, if you've taken some physics course or some basic electronics course, you would have seen them. And we want to visualize complex things in break down to simple things. Capacitance, we deem it to be simple enough, hence we are doing this. Okay, so yeah, that's about this. Let me just check. Yeah, I think I'm good till now. Okay, so till now I had just talked about, I've just brushed up on the MOSCAP and what we have been talking about in the previous, let's say, 1.5 sessions. Okay, if you still feel uncomfortable, if you still feel you want something to be repeated, please speak up, because now going forward I'll add uh, one level of complexity. We'll move one level forward and see how this, till now we are understanding how this device behaves when we apply a, let's say, gate bias. You are seeing that we're changing the gate bias here, right? And we'll add one more level of complexity there. Okay, so okay, just feel free to stop me anytime. Okay, just please always remember that. Okay, so what we are going to determine is something called the CV characteristics. C stands for capacitance, V stands for voltage. So you must remember Q equal to CV, right? Charge equal to capacitance times voltage, or rather, there are different ways of seeing it. The capacitance is dq over dv. Okay, so there are different ways of seeing it. Just keep it simple here. So we want to determine for this device that you're seeing on your screen, a metal oxide semiconductor. It's an ideal MOSCAP. We want to see how it behaves when we change the voltage. We are seeing that, okay, we already know that. We already know the four regimes, the flat band, accumulation, and your depletion and inversion. That is correct. We know that. But now we want to see the rate of change. Okay, till now we are seeing the absolute, that okay, if you apply this voltage, you will get this amount of charge, right? But now we want to see how it behaves dynamically. That means when you're changing the voltage, how will it behave, which is clearly visible in CV characteristics. Okay, so we know it's an ideal MOSCAP, and we are not applying any voltage, so what you'll obviously get is a flat band voltage. However, now let's say you apply a gate bias VG. So metal is denoted to positive side. And okay, so for our discussion, we'll assume this semiconductor to be P type. Okay, and P type semiconductor means an NMOS. So just remember that. And you can also see here in this, EF is closer to EV, so our substrate is P type. Okay, so now we apply a bias VG, positive bias. So what will happen? Accumulation will happen. We have already seen that, so there's nothing new that's I'm going to talk about here. So sorry, a negative. So here in this case, VG is less than 0. When VG is less than 0, you'll have an accumulation. So you see the gate is we are applying in minus Q is here, because VG is negative in this case. Okay, all right. So now let's just try to understand the picture here. I've already talked a bit about it. So what's going to happen here, you have just think of this oxide, the oxide that is here. So on one plate of the oxide, you have a negative charge. On the other plate, you have a positive charge. All right. Now, let's add one more level of complexity now. This VG was a DC signal. Now I'm applying a very small VS, an AC signal. So very small, I mean compared to VG. Okay, this means that this charge more or less will remain the same. It can increase or decrease a bit if I change Vs, and omega is the frequency of this, right? So this is the total voltage that I'm applying. What I mean when Vs is small, this is important. Vs is small in terms of when compared to Vg. So let's say Vg is 2 volts. Vs will be, let's say, 0.1 volts, 0.2 volts, not more. And omega is frequency of oscillation. Okay, frequency of oscillation of Vs. So let's just put some numbers. So let's say Vg we are putting at -2. Okay, and let's say Vs is 0.1 volts. Okay, so and this is yeah. So overall VA is going to move between minus 2.1 to minus 1.9. So overall, you will not see major changes, but some dynamic changes. The dynamics is the thing that we are interested in, right? Okay, so now what I'll do is, when I'm applying this small voltage, just for the case of discussion, I applied a 0.1 volts of Vs. So you'll see that a charge will accumulate here, depending, or increase or decrease. So I'm just denoting it only on the one side. So let's say I applied it from minus 2 I went to minus 2.1 due to the application of this Vs. So naturally more charge will accumulate here, right, on the metal pad. Correspondingly, a delta Q will also appear on the semiconductor side. Remember, this is a p-type semiconductor. P-type, so holes are readily available. They can quickly come to this interface, the oxide semiconductor interface. This is metal oxide semiconductor. And what you're seeing here, and again, I'll like you to recall that C equal to dq over dV. The differential expression for capacitance is this. So you're changing a voltage. What you're changing Vs. Vg remains constant. Vs is the thing that we are changing, right? And dq is, you measure this q somehow, all right? And thus we can have a capacitance, the capacitive action. In this case, which I'm calling a C accumulation because we are talking about of accumulation regime, C accumulation will exactly be equal to C ox, because you increase here, whatever change here in the charge is directly reflected here. So essentially you are saying that essentially what's happening, nothing is happening, is that this oxide is behaving like a capacitor essentially. Okay, and now let's plot this. So we are operating in Vg less than 0. Okay, one more thing, if you recall, at Vg equal to 0, exactly equal to 0, the capacitance is nothing but C ox. Okay, capacitance is nothing but C ox. So let's just say that, note the y-axis C over C ox. So if I say this one, this means the absolute value is C ox. And for accumulation mode, which means Vg less than 0, this is Vg. So Vg less than 0 is this. This will remain at C ox. C by C ox will remain 1. We have just talked about accumulation. Now, again, now I'll talk about depletion. I'll quickly go through. So now we are not applying any bias, right? So we should see a flat band, which we are good. Remember, p-type semiconductor. It's a p-type semiconductor. EF is closer to EV. We have flat band. Now what we'll do, we now apply a VG. In this case, we apply a positive VG because we want to deplete it. So we have seen this before. If you apply a positive bias, what's going to happen is that the holes will feel repelled from this, correct? And you can form a depletion region over here. You can see the width W. All right. Again, just like before, I'll add a small signal Vs on this, overriding this Vg. So the total applied signal is Vg plus Vs sin omega t. Omega is the frequency of oscillation of this small Vs. So how is it going to look like? Going to look something like this. If you apply, so let's say some extra charge you're putting on the metal here, that will get reflected over here. The width of depletion region will increase. All right. But if you now recall that the width of depletion region, I don't recall the entire expression. It was directly proportional to the built-in potential, square root of built-in potential. Okay, and remember, if there's field, if there's a depletion charge here, this built potential, you can see the bends are bending like this. Okay, so what I'm trying to say is that so what I'm going to say is, this is metal, this is oxide, this is semiconductor. So what's going to happen, let's say, where is the field dropping? So some field which you saw in the last session also, correct? We saw something potential dropping inside the oxide and potential dropping inside the semiconductor. So whatever charge is here, there are field lines that are emanating, field lines that are being started or ended from here, right? Some of these field lines will pass through here and rest will go in the semiconductor. Alternatively, you can say that, just so again you can see in this diagram, there's a capacitance that's riding over here, Cox, and another capacitance which is in series over here till the depletion region. So let me deplete it. This is the depletion region. So there are two capacitances that are in series, and finally it's a semiconductor. The circuit is complete. So two capacitances are two capacitances are in series here. Actually, this symbol I have put it wrong. So in series, the total magnitude comes out to be, so we call this Cox, we call this fellow as CW. So the total contribution comes out to be Cox parallel CW. So magnitude wise I am saying, so it will be 1 over C equal to 1 over Cox plus 1 over CW, because charge is distributed that way. Okay, so now let's try to plot it. We had already plotted it, C over Cox on y-axis, and one we saw was on the left side. It's the accumulation. How will it look in the depletion? Cox will not change. So when you're increasing your potential, when you change your Vg, keep on increasing your Vg in the positive side, it will get depleted, right? It'll start. We're not entering into inversion yet, just depleting. So Cox will remain constant. This fellow will remain constant, but this fellow, remember, is CW will be equal to epsilon A by W, right? So W will keep on increasing, CW will keep on getting smaller and smaller. Okay, hence this entity will will reduce in value, the total capacitance C. So it looks, when you plot it, it turns out it looks something like this. It will keep on dropping till it reaches something called a Cmin. We'll see what it looks like. Why does it not go below that? For now, just trust me that it reaches Cmin. We have completed a depletion. Now we come to inversion. Again, we see the flat band, no bias is applied. We apply some positive bias which is just enter into depletion. We increase the bias a bit more. Now we're in inversion, because in now C, EF is closer to EC at the interface, while in the bulk EF is closer to EV. This is inversion, and we see that an electron charge will appear over here. So how will it look like? The additional charge, what by mean, when you apply some positive voltage, some small voltage Vs, how will the charge get distributed over here? So how will it get distributed? If the frequency is low, if this omega is low, this means the electrons will get sufficient time and they'll accumulate at the interface. So this is metal oxide semiconductor. If the frequency is low enough, at low frequency CV, the electrons will get sufficient time to travel from the bulk of the semiconductor to the interface of oxide and the p-type semiconductor. So hence the additional charge delta Q that you're putting here, it will appear only at the interface. But this means this is essentially behaving like the only capacitance that you are seeing is the oxide. So in this case, in LFCV, the C inversion will be nothing but C oxide. What happens when you switch very fast? So let's so what's going to happen, it's at the so at this point we had reached in depletion. After this we see that C inversion is going to be Cox. This is the C by Cox line, so it's going to look something like this, connected like this, sharp jump. On the other case, when it's high frequency, so when it's high frequency, this means omega is high. When omega is high, the electrons will not get sufficient time, because see, it's flipping. So sometimes the charge has to be delta Q, the black region has to be above this blue line, sometimes it's below. So electrons will not get sufficient time to travel, to toggle here. So all the charge can only be contributed, the additional charge can only be contributed by the depletion region, right? And hence what we'll see, you'll see something like this. So let me just delete it a bit. Yeah, so what you see is something like this. LFCV, I told you, C in is equal to Cox, like this. While when you are here, the capacitance will change very slowly, and you will not see much change because it's already depleted. Remember that. And the total capacitance, if you recall, they are in series here. So 1 by C in will be equal to 1 by Cox. This is Cox here, and 1 over CW, right? And CW will be dependent on W, right? Epsilon A by, so this will be 1 over Cox plus W divided by epsilon silicon into area of silicon. Okay, So this W, if you recall, and this is in parallel with this, right? If this quantity is even if it's increasing, it's small enough, but only thing that, so its increase is not that perceptible. That's all I mean to say. When we work out some examples, you'll see. But that's the complete picture. The key takeaway here is that the frequency is low, but you'll see is that accumulation and inversion will have the same capacitance values. For high frequencies, it's not the case. High frequency, just it stays put at some minimum value, and it cannot shift much from that even if you increase the gate bias. Okay, so based on this, some basic understanding of how the CV characteristics look like, we are going to solve some problems. Okay, and this will be a sort of revision for what we had, the theory we had talked about. The question says, consider the CV plot as shown in the figure. What is the type of MOSCAP used? So first, as I have been asking you, just ask yourself, is this ideal? The question is silent about it. We'll assume it to be ideal. Second question is, which we must ask, what type of MOS? The question is asking that itself. So let's solve this first. What is the type of MOSCAP that has been used? Okay, so now we know that, so this is C, right? So if you recall from this diagram, okay, see, it has to be flat, that means in the accumulation region, and then a steep curve should come. So just look at what's happening at the negative voltage. So on the negative side, what we are seeing is that on the negative voltage, on negative voltage, we notice that capacitance is equal to C oxide. This flat line, you expect it to be C oxide, right? And on positive voltage, we notice that capacitance follows a curve to reach minima. This is the minimum that it's reaching, somewhere over here, which denotes a depletion trend. So it's depleting when we apply a positive bias. What type of semiconductor will deplete on application of a positive bias? Let's do that. So this is metal, this is your oxide, this is a semiconductor. So I'm applying a positive bias here, right? So if we have holes here, they'll get repelled and you'll form a depletion region. If it were N type and you apply positive bias, the electrons will get accumulated, right? That's not the case that's happening. Only when it's a P type semiconductor, the holes will get repelled away and you will form a depletion region. When you apply a positive bias, then only you will see a depletion region. This is a positive bias. This means what we are talking about is a P type semiconductor, and P type semiconductor means an NMOS. Okay, just to reiterate, on negative voltage we see C equal to C ox. So let's do that. If I apply negative voltage on a P type semiconductor, all the holes will get attracted to this oxide semiconductor interface, and we'll see accumulation, which is C here in the region 1. Okay, so this plot, the CV plot, corresponds to an ideal NMOS. All right, we have established now it's NMOS. Now the question is asked, what is the frequency that is used? Now we have already seen that this is high frequency. For low frequency, the plot in the inversion, right, the capacitance again rises to the C ox value. So this is your C ox value actually, this value that you're seeing here. But we see in this plot it remains at some minimum value. So the frequency used here is high, and we saw the reason also. The reason was that since the frequency is switching so fast that the electrons do not have time to come to the interface itself, the oxide semiconductor interface. Hence the only charge modulation that will happen, that can only be contributed by the depletion width, right, and which changes very slowly. Okay, hence you see a near flat line that you see over here. Okay, the third question asked is that indicate which one points correspond to which region. Okay, flat band corresponds to which region? We have seen that in our plot that this region is flat band. Sorry, flat band. Okay, so this region we saw was accumulation. Region 2 is the one that corresponds to flat band. 3 is your we'll see one by one. Okay, inversion we see is this, because when it has reached a minima, this means strong inversion has started, and it's high frequency, so it cannot retain the charge modulation, will only happen along the depletion width, and thus this region 5 denotes that the capacitance is not changing much. Okay, so region 5 is the one that corresponds to inversion. Accumulation, we have seen that this is an NMOS. So when we apply negative bias, right, when you apply negative bias, let's draw this. This is your metal pad, this is your oxide, this is a semiconductor, p-type semiconductor. So when you apply a negative bias here, negative bias, it's going to attract the holes over here. The holes will get accumulated at this interface, at the oxide semiconductor interface, and this is what we refer to as accumulation. And and the capacitance that this device will see when you apply negative bias, nothing is the capacitance of only the oxide, right, which corresponds to this flat line. So region 1 corresponds to accumulation. So that's what we'll write here. Finally, what we talks about the threshold. So we had in the previous session also we had talked about the threshold, and the depletion is started, then you reach inversion, and there is a strong inversion, right? So this point, so after the strong inversion, right, and you have defined the strong inversion as well, when phi s was equal to 2 phi f. Phi s, remember, is the surface potential, and phi f is the distance between your intrinsic Fermi level and the phi f is the difference between the intrinsic Fermi level and your intrinsic level in the bulk and the Fermi level in the bulk. So let me just write this formally. So phi s, I think I had already written that EI at surface minus EI in bulk, right, and phi f was your EI in bulk minus EF in bulk. There might be a change of sign here. I do not exactly recall the expression. Magnitude I clearly recall. Okay, so so that's when we said the strong inversion, or sometimes referred closely linked is the threshold voltage principle, right? So we are asked what is the threshold point. So threshold point is this point 4. This is the point where if in anything the depletion width changes are marginal, because the inversion has set in, and the inversion is strong enough so that any charge modulation on the metal pad that you do, right? So again, keep on drawing this metal, oxide, and p-type semiconductor. You are applying a large negative bias here. Okay, large positive bias. So holes will get repelled. You will form a depletion region first here. Okay, and this is the depletion region. Here it's in the bulk, it's still p-type. And what's going to happen at strong inversion, you'll see an electron sheet charge here. This electrons will start to get collected on this face of the oxide as well, right? And that's what we have defined as the threshold. This threshold, and after this, even if you modulate it a bit, right, all the modulation is going to come about at this oxide. In this region, all the charge modulation that's going to come, it will still come about here as well, because we are operating, remember, in high frequency. The charge modulation will come from here. But what I'm saying is that the bias points, the DC bias point 4 corresponds to your threshold voltage. Okay. Finally, the depletion, we know that this line where we saw that 1 over C is 1 over C ox plus 1 over C depletion. This expression that we saw. So here, whatever modulation, so this corresponds to 3. So we saw that the diagram looks something like this. This is our metal, oxide, and the p-type semiconductor. So we have applied some positive bias over here. Did I say negative in the? No, positive. Okay, so it has depleted. to a certain extent. And whatever charge modulation that you do here, so let's say you increase by some delta Q, so that charge will increase the depletion width over here. This will be again delta Q. The negative side, this is positive, this will be negative. All right, and so depletion width will increase, let's say from W to W plus delta W, right? And so charge will also increase. Remember, the charge stored here will be ND W plus delta W. Okay, so NdW plus ND delta W. This is delta Q that I'm talking about. So all the modulation on the positive charge on the gate will get reflected in the increase in depletion width that you see. So if the depletion width is increasing, yeah, this term CDEP will decrease. So 1 over CDEP will increase, and you just figure it out. And so as the depletion width increases, this term will keep increasing. Yeah, CDEP will keep increasing, and thus when you figure it out, it reaches to a minima because they are in parallel. Cox is remaining constant. Cox is being determined because we are not changing the thickness of the oxide or the electric constant. So this is Tox. This remains constant. Okay, you'll get some more clarity on what are the actual numbers, that when I say they don't change much, you reach a minima. Are we really reaching a minima, or this is some fancy thing we are talking about? When now we are going to solve some problems in a minute or two, then I hope you'll be able to clearly appreciate what I'm talking about here. How do these CV curves behave? Okay, so again I'll take a pause for a couple of for a moment. If you want me to repeat anything, some region is not clear, flat band, depletion, inversion, and so on, from this looking at this CV curve, we can get a lot of information about a MOSCAP, which we'll see in a couple of problems. And when we'll also introduce the non-idealities, then this single plot becomes very handy. We extract a lot of information from this. All right. Okay, then no comments, then let's go ahead. So this question is just whatever understanding that we have, this tends to summarize that. I've been repeating these terms and again and again, but this question formalizes essentially that I've been trying to say. So the question asks, which one of the following are correct in reference to CV measurements? So again, if nothing is given in the problem, let me just a second. Yeah, okay. So if nothing is given in the problem, we'll just assume that it's an ideal MOSCAP. And here the question of whether it's NMOS or PMOS doesn't arise, because the question does not specifically ask us to delve into that. It just asks of the nature of because nature of PMOS and NMOS will remain the same, right? It's just the charge carriers, so holes and electrons, that's the only difference. The question asks, statement 1 says the capacitance of a MOS capacitor in strong inversion is larger when measured at high frequencies than at low frequencies. So what it's saying is that, so C inversion, so this essentially asks C inversion for high frequencies is larger than C inversion of low frequencies. This is statement 1. Statement 2 says at low frequencies there is enough time for generation of carriers in the depletion region and the movement of inversion charges to the oxide silicon interface. So what's it saying? Let's draw that metal-oxide-semiconductor diagram again. This is your metal, this is your oxide, this is your semiconductor. So it's already depleted. And when you so this is a p-type semiconductor that I'm assuming. Okay, so you're applying a positive gate bias here. You're applying a positive gate bias, it's already depleted, and when you put a small charge, so what's going to happen is that for a low frequency, so an electron, and it's already inverted, okay, so there's a sheet of electrons that's already present here. It's a sheet of electrons. So what it's saying is that at low frequencies, there is sufficient time. This means voltage is not changing fast enough, and the electron will have sufficient time to be generated here and then travel here and add to this, behave like delta Q. Polarity is not changing, let's say, so it was adding a delta Q here, right, and this delta Q remains here. So electric field lines reach, and there's sufficient time for the electron to get generated in this depletion region and travel here, right. If in the meantime, if it switched back to, let's say, minus delta Q, then the electron has to travel back. So there's sufficient time to do that. It can come here, it can reside, and then only this will flip to minus delta Q, and then this electron can go back, okay, which is possible only at low frequencies. So we see that statement 2 is correct. This is what I have been arguing the whole time, that the electron at low frequencies, the charge that you are putting at the gate, it will stay there for long enough so that electron will get generated here and can move to the oxide semiconductor interface and thus can contribute there. So the only capacitance this extra delta Q is seeing is just the Cox, right? That's what I've been saying. So this is the picture in terms of charge. Here on the bottom I have drawn a diagram in a different way, so to speak, right. Here it's just a charge diagram. So in the low frequency, so whatever extra charge that you're putting, which is denoted in black here, right, on the metal pad, it gets time to reflect it over here in the, so negative is your electron sheet charge. So this you see here, this is your electron sheet charge, okay. At low frequencies this is possible. At high frequencies, if you put a charge here, right, the electron will not get sufficient time, so the depletion region has to provide that extra charge. So this extra charge that you see in black here has to be provided by increasing the width of depletion region in case of high frequencies. So what capacitance it will see? It will see this capacitance and in series with this capacitance, Cox and Cdap. In low frequency, the delta Q sees only Cox, okay, and we had drawn this in this fashion. So at high, so after the strong inversion, the low frequency CV capacitance will again be Cox. So C by Cox is 1 here, while for high frequency, the extra charge, the capacitance, is nothing but a combination of Cox and Cdap. This is Cdap, and thus it will continue to be a flat line. So what we see is that C inversion HF, is it greater than C inversion LF? No, C inversion LF is greater. This is the inversion region over here. This is inversion region, right, and we see LF is greater. Statement 1 is false, this is false. Statement 2 is true. 1 is false, 2 is true. This will be your correct option, okay, right. So okay, again a very similar problem with the plots that now we are familiar with. Consider a MOS capacitor with p-type substrate. Again I'll assume it's an ideal, so if it's a p-type substrate, it will be an N-MOSCAP, and we'll assume it to be ideal. The LFCV and HFCV are identical in which regions? So this is the plot that we are seeing. So the solid black line is your LFCV, and the dotted red line is HFCV. So you can see that this is the accumulation. It's a p-type substrate. So on the negative side, so let me draw that again, metal oxide semiconductor, and I want an accumulation region, okay. So what means I'll apply negative bias. This is a p-type semiconductor. So if I have a negative bias, excuse me, right, so if, just a second, can we say 0.4 also considered as depletion region? Okay, so there's a doubt regarding some, yeah, so in this region I was so the questions is asked that the 0.4 can we say to be a part of depletion region. Okay, the thing is that inversion technically is also depletion, but we are making a strict boundary here, right, that at threshold, okay, at threshold we'll say that depletion has ended and inversion has begun. So we're making a very stubborn definition, so to speak. it will not, it's not so smooth ideally, but even for this, in an ideal MOSCAP, there is depletion at let's say zero point 0.4. But just for the sake of creating some boundaries, so that we can understand this complex device, break it down. Okay, so that's how we are making these definitions for our own understanding, so that we can communicate better. But to an extent, you are true that point 4 is a part of depletion, and for the same argument someone can argue it's also part of that inversion also. Yes, but if I have to choose between 3 and 4, which is more representative of depletion region, I'll say point 0.3. I'll put it that way. Okay, right. So where were we? Okay, yeah, this one. So I was saying that if you apply a negative bias on your metal pad, so all the holes will get attracted over here, and you will see a whole sheet. This will be a whole sheet charge, I mean. This is what we refer to as accumulation, right? This will happen in low frequencies as well as high frequency, because they are in such a high concentration and they are very near to this interface. They can quickly come irrespective of the frequency. So that's what you see here, that, and the capacitance they only see is the oxide, right? And any charge modulation that's going to happen here, so this will be minus delta Q and plus delta Q, it will only happen across this oxide as the dielectric. So you see C by C ox is 1 irrespective. So in accumulation regime, what we'll see is that at high frequency, low frequency will overlap, right? In depletion also they'll overlap, right? And where they'll not overlap is the inversion, because we had already discussed that for high frequency it will not find the electrons in that case will not find sufficient time to come to the oxide semiconductor interface. All right, so in that case they'll differ, but they'll overlap in accumulation, depletion, but not in inversion. Okay, so the correct answer would be wait 1 second, not inversion, so accumulation and depletion. Sorry. So this will be your correct option. Accumulation and in depletion, the curves will overlap, as you can see here. The reasoning is the thing that I'm repeating them. I know you might be like, okay, we have understood, you're repeating these points over and over again. I know. I want this to be like very clear whenever you hear these terms, that you should make a picture. So in the last class, we were doing it through the, if you recall, those through the depletion region plots, where we saw a depletion region in a different color, and the charges were in a different color. There, the blocks that were there. Here I'm drawing the metal oxide semiconductor, and here I'm showing the primary aim of drawing this diagram is to show, just to illustrate that the holes have to travel. So if holes are already here, they don't have to travel much. However, when we say in case of so what I mean here, electrons had to travel from this point to this point, right? This is why I'm drawing these different diagrams. Whichever suits your understanding, comfortable with, just have a clear picture in mind. That's my aim. Different, it's the same way of, it's a different way of saying the same thing. You can understand it through the CV plot, you can understand it through this charge distribution diagram, you can understand it through this plot. This is again a charge distribution, so to speak. Different ways of speaking the same thing, doing the same thing. Here I was also denoting the bias as well, to illustrate and the semiconductor type, to illustrate whether in accumulation or inversion, whatnot. Just try to feel comfortable, and I hope you feel comfortable when you practice your problems from this course or whatever course you have at your college. So that's the aim. Okay, so now we will actually hopefully put some numbers, right? Let me just check. Yeah, so now we have entered the numerical regime. Numerical regime, I mean, we'll get a feel of the numbers, as I've been telling you that, like, you can get a grasp of theory but you'll able to appreciate it when you put some numbers behind them. So for instance, we talk about intrinsic carrier concentration. We keep on talking, but when you put in the numbers that in for silicon it's 1.5 10 to the power 10 at room temperature cm minus 3, we dope it at 10 to the power 16, so we can clearly see this 6 orders of jump there, right? So doping, all these terms, when you're talking it, it's fine, but when you actually uh, have a feel of the numbers, then you understand the concept in much more detail. That's what we'll try to do here. Okay, question says that consider a MOS capacitor CV characteristics as shown in the figure. So you have it here. The capacitor comprises of a metal gate with a work function of 5.62 eV. The gate dielectric is SiO2 with relative permittivity of 3.9. Assume there is no fixed charge in the oxide. So again, the question is silent about the whether it's ideal or not, but it gives sufficient hints. So no fixed charge in the oxide means the oxide is, I mean, it's a good insulator. We are talking about SiO2, so we assume there are no traps, no fixed charges, no anything. We'll assume that it's an ideal MOS capacitor. Okay, and now we are required to find, we have seen this plot over and over again. So first, the first thing that I do is that it's NMOS or PMOS. So we will again do that exercise, although this question doesn't ask, but we must ask ourselves whether it's NMOS or PMOS cap. So the now you must have an idea that if it's flat on the left side of Vg less than 0, then what we are talking about here is a straightforward thing, that this means Vg is negative here, and you see only a Cox, right? This means an accumulation is happening. So again, I'll write that accumulation for Vg less than 0. Now this will happen only when we have a p-type substrate, p-type semiconductor, because if you have, I'll draw this diagram again, you have the metal here, you have the oxide, and you have the semiconductor, right? If you apply a negative bias here, so you have plenty of holes, this is p-type, they'll readily come and accumulate here, and what you will see, you only see Cox, right? On the negative side, you apply any bias, the picture will remain the same. That's why on negative bias you only see one thing, Cox. Okay, and we also know that for high frequencies it goes to a minima and then it saturates over there. So 2 corresponds to high frequency CV. Do I have a diagram? No. So we have seen this diagram plenty of times. So first, it's an NMOS or PMOS. It's not a PMOS, it's an NMOS cap, and we are assuming it to be an, for now, at least for this part, no fixed charge, at least it's partially what we say ideal, maybe not completely, let's see. So the question 2 is HFCV, we know that comes to a minima and then saturates there, while for LFCV it can again go back to the Cox, because inversion charge will have, the electrons will have sufficient time to get generated in the, and then travel from the depletion region to the oxide semiconductor interface. So first corresponds to HFCV and second corresponds to sorry first corresponds to LFCV, this is LFCV, and second corresponds to HFCV, right? Okay, so we have done the first part. Second says that if the area of the capacitor is 2 into 10 to the power minus 3 cm square, then the oxide thickness is, okay, so remember that this point is nothing but Cox. I think I did it in the, yeah, so this was oxide, correct, this was oxide, and the accumulation, but we have the whatever capacitance that we see is only due to the oxide. Okay, so essentially this is the accumulation, and we see the charge modulation that you are seeing is happening here, right? Since a negative bias, so if you apply a delta Q charge on the negative side on the gate, positive charge will appear on the, this is due to the holes present in the p-type semiconductor. Okay, so the capacitance, and this is the curve that we have, it's essentially the same curve that we see here, but what I mean to emphasize is this point. So in accumulation, I can write C accumulation, which is this regime, is equal to C oxide, and this is the expression that we are using. Okay, so everything is given to us. Okay, So Cox, what we see is 150 picofarads. Let's put those numbers. So 150 picofarad equal to epsilon naught is 8.85 10 to the power minus 14 farad per centimeter square. Epsilon oxide is given. Silicon dioxide is 3.9 permittivity. Area is also given, 2 into 10 to the power minus 3 cm square. So everything here is in centimeters. Please remember, T oxide, this T oxide will also come out in centimeters. You plug the numbers and hold on a second, I'll get my calculator. Alright, so it's 8.85 into 3.9 equal to, that's 34, and that's okay, into 2, so that's 69 into 10 to the power minus 17. Yeah, 69 into 10 to the power minus 17. 69 into 10 to the power minus 17 divided by let's do this 0.15 into 10 to the power minus 9 centimeters. So this will come out to be 0.5 460.2 into 10 to the power minus 8 centimeters. So let's call this as 4.6 into 10 to the power minus 6 centimeters. Okay, so that will be 46, no, 4.6 into 10 to the power minus 8 meter, 46 nanometer. 46 nanometer. 46, 45 we have. So this will be the answer. All right, as I've been saying, if you know the formula, anyone can solve this. What is the understanding that we have here? Then the key takeaway from this problem is, first of all, the range of values that you see. So typically the capacitance values that you see are in picofarads, and now today the practical values are even in femtofarads. Okay, and one of the other key things that you must take note here is the thickness, oxide thickness. We're talking about the regime wherein tens of nanometers, 45. Today it can go to even lower values. Okay, less than tens of nanometers, which has its own problems, but yes, it can go essentially. That's the feel of the numbers that I was saying. Okay, maybe we'll see a few more numbers today, not just this. Okay, so let's go ahead, and now the questions asks is to calculate the depletion capacitance. Okay, so as someone was asking, the depletion which we see in this sloping region. So this we refer to as the depletion region, and let's denote it by our good the charge distribution that we have. So in this case, what's going to happen is that now you're going to apply positive bias. You can see the Vg is positive. Let me draw the diagram again. So we have this metal pad, you have your oxide, you have this p-type semiconductor, and you're applying a positive bias. Okay, so what's going to happen, you must have repelled away some of the holes, and which will expose the underlying. This is a depletion region. Let's say it's with this W, and again essentially what you have, just like in p-n diode we saw, there's a charge that is being distributed, and there will be capacitance that we associate with such. We model them with a capacitor. Okay, so any additional charge and let's say delta Q that you put on the metal gate, now that has to be counterbalanced by a charge, and which will be accumulated here, denoted by delta W in this region. So that charge, any plus delta Q that you put on your metal pad, I repeat, will be equal in magnitude in the depletion region. So its width, depletion region's width is bound to increase. Okay, so now, and this is the region that I have been saying, that this region is the depletion thing. Same picture over here, right? And I've been saying one more thing, that this value that you see, Siemen, it's like here, See, its counterpart here is given as 25, and C min is nothing but when C aux and C dep are in parallel. So let's do that. I mean, they are parallel but effectively in series, but how their magnitude is calculated is through this. So I can write now 1 by 25 1 by C aux plus 1 by C dep. Okay, let's solve this here. So C dep, rather 1 by C dep, I can write as 1 by 25. What is C aux? C aux is nothing. C by C aux is 1 here. So this value has been, this is nothing but 1 over C aux. Okay, so C dep will from here come out to be, if you take 150 as LCM, 150 over this is should be 6 minus 1, so that's 5. So this is going to be 30. And the units are picofarad. So the area term doesn't come here because everything is in capacitors, right? And the capacitance itself was given in picofarads. So what we determined that the depletion capacitance is 30 picofarads. So which is like this. Another thing to note here is, I think it will come in the next set of problems. What is the depletion width? Typical depletion width that we see, right, when we apply, let's say, a nominal bias here, whatever that is, the depletion region. But the key thing to the takeaway from this problem is that C aux and C depletion are comparable, right? It's not that one term is dominating, right? They are comparable. And let's just try to do one more exercise. Okay, so what I'll do is that let's just see that if I increase the depletion capacitance from 30, let's say 10% increase, from 30 to 33, how will C min change? Okay, how will the capacitance change? So let's just try to do that exercise. It's not a part of this problem, but I just want us to have a feel. I also don't know, I just thought that it would be good exercise to do. So what it will be? It will be 1 over C, right, should be equal to 1 over 150, which is C aux, plus 1 over, let's say, 33. Okay, so from C will come out to be, calculator, it will be 150 times 33 over 183. It's coming out to be 27 picofarads. So when I apply the when I increase the depletion capacitance, okay, by increase the depletion capacitance means, so remember, depletion capacitance is your epsilon A over W. So when you're decreasing the depletion capacitance, means you're decreasing the depletion width. Okay, you're moving in this direction. So C should increase, which we are seeing. So from 25 it went to 27. This means I'm at somewhere this point here. This point. If I reduce the depletion width even further, okay, you will see the C dep will increase. If C dep will increase, its contribution, if C dep will increase, and this point will keep on moving in this direction. Okay, and now let me just on the other side, let's just reduce the depletion capacitance. Okay, I'll denote it in green color. So if we reduce the depletion capacitance, then again, let's say by 10%. Okay, so 1 over C, it will be 1 over 150 plus 1 over 27. Let's say what kind of C minimum in that case, which we'll see. I'm really pushing the limits because essentially once you are here, inversion will kick in. So what I'm doing is will actually not happen. I just want to see that how much is the percentage change in C minimum. That's essentially that I'm doing here. Okay, 115 to 27 or 177. So that comes out to be around 23. So in that case, C minimum will come out to be 23 picofarad. Another key thing that you should note, that C minimum is primarily being determined by the depletion capacitance, not by the oxide capacitance, right? Because you see, in the case that was given in the problem, the C minimum was 25 picofarads, C depletion was 30 picofarads, right? In my in my, let's say, hyped up case, the green case that you're seeing, so when the C depletion was 27 picofarads, you see C minimum was 23 picofarads. Essentially, the larger value will get ignored because the capacitance is here we are treating as 1 over C's. So the larger capacitance value, when you invert it, will have lower component. Okay, but the key thing that I want you to take away from this example is that C minimum is more closely related to depletion capacitance than to your oxide capacitance. Okay, that's the key thing that we're learning from this exercise here. Okay, right, some more numericals. So here, this is from gate, not too far back. This is what, 2023, yeah. So 1.5 years ago this was asked. The question says that an ideal MOS capacitor, let me change the color just a second. An ideal MOS capacitor, so ideal is given, so no need to, I mean, it's the test that I do, whether it's ideal or non-ideal, it's given, and also it's a p-type semiconductor is given. So p-type semiconductor means it's an MOSCAP. Very good. So life is simpler for this problem. It's shown in the figure. It is under strong inversion, so they're already saying that it's under strong inversion. Strong inversion, so if it's a p-type means it has to get depleted, so we must apply a positive gate bias to deplete and obviously to invert. Hence the VG is given as 2 volts. Positive bias is given. Okay, the corresponding inversion charge density is 2.2 microcoulombs per centimeter square. So what we are saying here essentially is, when you apply a plus 2 volts, okay, obviously you would have depleted it. So I'm depleting it. Okay, and it has a inversion charge. So this is given Q in as 2.2. Mind you, this will be negative. This inversion charge will be of electrons. This is a p-type semiconductor. Okay, so inversion will be of electrons. So this will be minus 2.2 microcoulomb per centimeter square. There will be sheet charge obviously here. This will be of some positive magnitude, plus Q, whatever that is. That will be balanced by these charges, this sheet of electrons, as well as in this negative depletion charge due to the lattice acceptor ions in this case. Okay, right. So this is the picture for at 2 volts. Now what they're saying is that now we want to increase the bias to 4 volts. So when you increase the bias to 4 volts, plus 4 volts, so let's say this will become plus Q2. So earlier this charge was Q1 over here. Now what's going to happen, and let's call this Q in 1. So in the blue color, what they're doing is they're increasing the bias now. So if they're increasing the bias, let me increase the charge. So this total charge I'm talking about is Q2, not the blue and the red is itself Q2. And naturally what's going to happen is this charge, let's draw this box again, metal oxide, this is grounded, we have plus 4 here, this sheet here is Q2, and this sheet here is Q into, and the depletion region will not increase because we are inverted. Okay, so all the charges now, electrons will come to the oxide semiconductor interface. So we are required to find this Q into. For Vg equal to 4, the approximate Q in is. So how do we do that? So it's so what you need to understand is, after the threshold has been reached, all the increase in charge, right, is driven only by this capacitance Cox. Correct? We have seen that. I'll repeat that. After threshold, all the modulation in charge is determined by Cox, because you see all depletion charge is not changing, it's the same for both of them. It's only Q in 1 and Q in 2 are different due to the Q1 and Q2 being different, correct? So everything is being all the action is happening across Cox, that's it. Okay, right, but remember the keyword after threshold. So how do we write it mathematically? So this is again the same picture in the charge regime, so to speak. This is how we write it. The Q in the inversion charge, all the action is happening across Cox, but only after certain threshold, right? So delta Q, so to speak, will be Q equal to CV, you know, but here the V will essentially be only after the threshold, only that voltage will be counted. Okay, so what I'll do is that I'll write it in red first. So Q in 1 will be equal to Cox Vg1 minus Vt. Vt is not determined by your gate voltage. Okay, it's inherently depending among many things. It's dependent on oxide thickness, for instance, the permittivities and the doping as well. Okay, and obviously the ideality that we assume that metal and semiconductor have the same Fermi level. So Vt depends essentially on that, but not on the gate bias per se. Okay, so we can clearly write this expression. Okay, and from this, just let me see, I think we are good. Yeah, we think we're good. So from this we can get Vt. So from this Vt can be achieved as, so Vg1 minus Q in 1 over Cox. Yeah, so Vg1 is given as plus 2 volts, the bias. Q in 1 is also given 2.2 microcoulombs per centimeter square, and Cox is given as 1.7 microfarad. This is per centimeter square and per centimeter square. From this you can get Vt. So Vt will come out to be, hold on a second, 2.2 by 1.7, that's 1.29. 2 minus that, it's 0.706. So Vt is coming out to be 0.706 volts, right? And as I've been saying, this Vt will be the same because the device is not changing, it's only the bias that you are changing. Okay, so now I can write Q into is Cox Vg2 minus Vt. Cox is not changing, it's the same device. Vt is also not changing, it's the same device. Cox is again 1.7 microfarad per centimeter square. Vg2 we are now putting a bias of 4 volts minus Vt is 0.706. Okay, now we'll do one more thing, but let's just get this answer first. So 4 minus answer by 1.7. Yeah, so it's coming out to be 5.6 microcoulombs per centimeter square. So this so this answer is 5.6. Okay, what do we understand from this? Couple of things. First, hold on a second. Yeah, first thing is that this expression that you're seeing, valid only for Vg greater than equal to Vt, which makes sense actually, because the inversion charge will only come after you have crossed the threshold. We've seen what do we mean by threshold, strong inversion and so on. So this expression will kick in only when Vg is greater than equal to Vt, which also makes sense. If you put Vg equal to Vt, you should not get any inversion charge because the inversion is just starting there. If you put Vg equal to Vt, you can see that what you are getting is essentially the zero inversion charge you're getting at 0, right? The other thing which we note is that it's a linear relation, and that's a good point to note actually. What it means is that just by let's say rotating the voltage knob at metal, you can control the electron charge in a linear fashion. Okay, not in a quadratic, not in square root. It's a linear relation that is between the voltage, the gate voltage, the control that we have, and the charge that we are seeing at the interface. And obviously, if we have some other mechanism that we can use this charge to drive a current, that's for a MOSFET. For now, that's our understanding, that it's a linear relation that we are getting. Okay, so those are two things that we should, that you may keep in your mind. Just give me a second. Excuse me. Yeah, okay, so that's that. And then the next problem. Okay, any doubts or comments about this? Because this was slightly different from what we have been doing. It was inspired from the fact that we have inverted the semiconductor and then we built on. This is a concept we have been talking about, inversion charges, but this is the first time that we put some numbers to it. So it's that's why I'm saying, it's when you solve some numericals you get a feel what exactly are we talking about. Okay, so let's move forward then. Yeah. Okay, another numerical that is based on the understanding also from gate. So in this problem it says that in MOS capacitor with an oxide layer thickness of 10 nanometers. So this is the TOX that is given to us of 10 nanometers. In the one of the problems, you remember, it was 45 nanometers. And as I've been saying, that we are entering into single digit nanometers now. Beyond that, it's just if you go, so for instance, 1 nanometers, you will try to hit only 5 layers. Okay, when you go into that, very the idealities of the oxide layer that we had assumed, they start to break, right? We'll assume it's ideal in this problem. Okay, question is silent about it, but we'll assume it's ideal, this oxide 10 nanometers thick silicon dioxide, and the maximum depletion layer thickness is 100 nanometer. Okay, so we are given also the depletion layer. This means that if you put, so the depletion layer can only go to 100 nanometers. Let's say if you put more charge on the gate, on the metal, then it's going to get inverted. The depletion layer will not extend any further. Okay, and the permittivities of semiconductor and oxide are given. I think it's 1:3. That's typical of a silicon. Okay, so we just saw that permitted to silicon dioxide is a 3.9, and silicon would be I think somewhere around 11.9 or 12, something like that. So that's where this 3 ratio comes out to be. Now we are required to find the ratio of maximum to minimum capacitance. So for that we need to invoke our CV plot. So if you recall that, as I've been just saying, this is a depletion. We'll assume the PMOS, sorry, the NMOS. This means P-type substrate. P-type substrate, if you put a positive gate, the holes will get repelled. You will get a depletion region. And if any modulation you do of delta Q charge, and if we are only operating in depletion, this means you have not entered the inversion yet. Then it has to be counterbalanced by the modulation of the depletion width. Okay, and this is what this is the plot, the CV plot that we have been seeing of an NMOS. Okay, right. So now maximum to minimum capacitance. So from this plot you can clearly see the maximum capacitance is nothing but Cox, C over Cox. Remember, the y-axis is C by Cox. The maximum value is going at 1. It's in accumulation. Also, it's the same thing when you are in inversion. Right? So C max can be C oxide. Right? Similarly, C minimum that we see over here. Right? C minimum will be achieved and the depletion width cannot extend anymore. Right, this is the maximum that depletion width can go. So 1 over CDAP will be your depletion width cannot extend anymore, so your CDAP cannot fall, and thus your C min, which is Cox parallel CDAP, cannot drop any further and you reach a minimum point. Okay, what we are required to find is the ratio of maximum to minimum capacitance. So let's do that. C max over C min will be nothing. C max, the value is Cox, The value of C min is Cox parallel CDAP. Okay, CDAP is your depletion capacitance, FII. Okay, so let's do that. So I just opened the expression for of the denominator, that is Cox CDAP divided by Cox plus CDAP. What's going to happen now, this will get cancelled with this. What you'll get is this Cox plus CDAP over Cox, and then you will divide Cox over both the terms, so we'll get 1 plus CDAP over Cox. So what are CDAP and Cox? This is nothing but this. CDAP is epsilon A by D, capacitance. So epsilon naught, epsilon S of the semiconductor, and A. So this is your oxide, this is your semiconductor metal. Okay, so let's put these values. So this will be 1 plus CDAP is epsilon naught, epsilon S A over TDAP over Cox is epsilon naught, epsilon ox area over Tox. The cross sectional area is same for both. Epsilon naught and A get cancelled, so what we are left with is 1 plus epsilon S over epsilon ox and Tox over TDAP. Actually, we know both these numbers, so epsilon S plus epsilon ox is given as 3. Tox, oxide thickness is 10, depletion layer thickness is 100, both are in nanometers. Okay, so what I'll get here is, just a second, am I making a mistake somewhere? Just give me a minute. Right, so this will be this gets cancelled, so what we'll have is 1.3. okay, let's just see if we didn't do anything wrong. Yeah, okay, I think this looks good. So what we are getting here is no, something is wrong, because remember in the last problem where we got Cox was 150, C minimum was 25, so the order was higher there. So I'm thinking, did I make some mathematical or conceptual mistake? Let me just go through the problem again. So we are required to find the ratio of maximum to minimum capacitance. So maximum capacitance would be hold on a second. Yeah, so maximum capacitance is nothing but Cox, which is correct, and the minimum capacitance will be achieved over here, which is nothing but Cox, because this oxide is in parallel. I mean, it's in series, but we'll denote it with parallel to CDAP. Alright, so the Cox by Cox CDAP over Cox plus CDAP, that's correct. Cox gets cancelled, Cox plus CDAP comes into the numerator. Oh no, I think I made a mistake here. Right, Cox plus CDAP will be Cox times CDAP over Cox plus CDAP. Right, yeah, so no, actually it's correct. Okay, I think conceptually I'm fine, but the answer keys, my answer key says something different. So I'll make a correction if I find anything in this. All right, but that's how we are doing this. So the way we did this was, we just knew what how the CV plot for an ideal MOSCAP looks like, and we also knew that the maximum capacitance that we can have is nothing but oxide capacitance. The minimum we can go is we can have is up to when just at the onset of inversion, that is Cox, when it's in this series component with in the depletion capacitance, and the capacitance in series are denoted by a parallel notation. So 1 over C min is nothing but 1 over Cox plus 1 over C dep. So that's how we did that. We put all the values over here. Cox gets cancelled, right? And yeah, Cox gets cancelled. Just a second. In denominator, oh yes, thank you very much. Thank you very much. Denominator is C dep. Yeah, denominator, this is C dep. This will be Cox then. Yeah, 1 plus Cox by C dep. Thank you very much. So let's erase all this. Yeah. Okay. So this is oxide, Tox. This is and denoted by divided by T dep. This will come out to epsilon naught, and area will get cancelled. What we'll get is epsilon ox, epsilon s multiplied by T depletion by T oxide. So oxide by silicon is given as 1 by 3. So 1 by 3. T depletion is 100. T oxide is 10. So that will come out to be 10 by 3 is 3.33 plus 1 is 4.33. The ratio that I'm getting is 4.33 here. Point. Thank you for pointing that out. Okay, so yeah, so that's what I was coming, because in the previous problem that we had solved, we are getting a ratio of approximately 6. So we should not be like the numbers are more or less similar. In that case, we had 40 nanometers of, what, 45 nanometers of, I think, this what do you call the oxide thickness. Here we are 10 nanometers. So the we are nearby, so that's why I suspected something was wrong. Okay, yeah, so that's that. Okay, one more thing. You few of you might be opting to write gate. Quick suggestion about that is that the gate, on the numerical answer type problems, they usually ask you to round off, right? So for instance, if they were asking you to round it off to one decimal place, you must write it as 4.3. Be careful about it. I mean, half a mark can decide your rank to a great extent. So if you solve the problem correctly, just rounding it off clearly should not ideally make a mistake there. Okay, so till now I've been talking about the ideal MOSCAP. We had seen these assumptions many times, and I told you we'll violate the first one and the second one, because these are, I mean, the real problems that we encounter. So let's do that. So first case, when the metal semiconductor phi ms work function is not 0. I mean, the difference is not 0. This means the work function of metal is not the same as semiconductor, which you see here. So Fermi level of metal is here, semiconductor is here. We have not joined them yet, so there's some, let's say, E vacuum here. E vacuum. So this will be your phi m, this will be your phi s, and as you can clearly see, if when I bring them together, the electrons will flow from metal. I mean, not flow, because assuming it's a perfect oxide, so the bands will bend, right? And the bands will bend something like this. So what you're seeing is that even if you're not applying any gate bias, right, what we are seeing in this case, so this is a p-type semiconductor, right, we're still seeing some depletion. You clearly see the bends are bending, and the material at the interface, at this interface, right, is behaving intrinsic or maybe even n-type without the application of a bias, right? So what we do in this case is we deliberately apply some bias, right? We deliberately apply some bias to make it flat again. Okay, it's very simple to understand. Whatever the error that has been introduced into the system, I'm calling this an error, but this is a facet of whatever the reality that has been introduced in the system, we offset it by the same margin by applying a gate bias. Okay, so Vg equal to 0 was this, right? So if I apply a negative gate bias, so to speak, right? If I apply negative gate bias, the VG will shift, Fermi level will shift up. If I apply a negative gate bias of the same amount as phi m minus, the difference was phi m minus phi s, right? We'll again achieve the flat band. That's what I'm doing here. Mathematically, right? So what I'm doing is this expression that you see is of VT. Professor Naresh has explained it, of an ideal MOSCAP. If you add phi ms to that, you get VT with correction for work function difference. So if phi ms is 0, this is what we expect to get actually. Same thing is happening here. So whatever the error, not the error, whatever the reality has been introduced into a system, non-ideality introduced into the system, we offset it by the exact same margin. So we are again to flat band. Okay, once you have flat band, then all our concepts like you apply a accumulation and your depletion and further inversion, those concepts can still be applied. Just that you need to achieve flat band. That's our only aim now. Second non-ideality is when oxide charge is not zero. We have been saying that the oxide charge is zero and so on. No. Usually what happens is some positive charges do get trapped inside this oxide layer. So remember, this is the oxide layer that we have, right? And you can see the phi ms is still there. So what's going to happen is that again you'll see that when you bring them close together, even with the application of any gate bias, right, what might happen is that the bends might bend. Again, here there are two non-idealities. Okay, so just the cumulative effect will be there. Again, we'll do the same thing. We'll apply specific that gate bias which can offset these non-idealities. Phi ms we already introduced, and we are assuming that we are introducing a positive trap charge of Qi. Then we simply apply a gate bias which can offset it. So whatever non-ideal is introduced here, we apply a gate bias corresponding to that, right? And again, so this is the VT. So this is your ideal. This is your ideal VT, and you have offset by that amount. This band, this voltage that we are applying to achieve the flat band condition, to achieve this condition, is also known as flat band voltage. Very, easy to remember name. It's its function. So let's quickly, we're running out of times. I want to solve a problem or two of this. So let's quickly do this. So total charge trapped in the oxide region is 80 picocoulombs. All right. And the area is given, the permittivity is given. What is this metal-semiconductor work function difference? So we know this. Okay. What's happening is that when you don't have, how should I say this? Okay, let me go back. So it's going to happen in this scenario, right? So whatever CV that we have been habitual of seeing, right? We have been seeing this kind of CV. Sorry, bad drawing. Let's consider a low frequency, okay? C and V. In flat band, in non-ideality, this is not the case. This gets shifted. So that's what I'm drawing now. Can either get shifted to the right or left depending on the value of VFB. If VFB, this entity is positive, you will get a green curve. Okay? The red curve is the ideal one. If VFB is negative, right, but then you will get, because VT is now shifted to the left essentially, a more negative voltage, then you will get is something which I'm drawing here in blue. Okay, so the non-ideal curves look either like green or like blue. Okay, that's how the non-ideal CV curves will look like. Here, a non-ideal CV curve is given to us, because we can clearly see the question asks about metal-semiconductor work function difference, as well as it says it has some trapped oxide charges, right? But we clearly see that this point where depletion starts is coming at exactly at 0. How is this possible? What's happening is that these two terms are cancelling each other out. So if this term is 0, we get ideal CV curve. Here, this curve also looks like ideal CV. That is possible only when this voltage, is also known as V flat band, is 0. We put it 0, phi ms equal to Qi over Cox. Phi ms we require to find. Qi is given as 80 picocoulombs. Area is 4 into, okay, wait. That's the charge, sorry. Cox will be given by 8.85 10 to the power minus 14 epsilon naught epsilon s, which is 3.9. Area is 4 into 10 to the power minus 3 over epsilon a over d. What we need is the thickness. Okay, hold on a second. Yeah, Cox is given as 200, because remember this value is nothing but this value is being is this corresponding to Cox. Okay, so I need not do any of these things. Let me just delete that. So this will not come actually at all. So what's going to come? The value of Cox, which is given by 200 nanofarad per centimeter square. Okay, the units have to match. So this is Q. Yeah, so if this is coulombs, this has to be farads, which is not the case, so we must multiply it by area. This will be 80 picocoulombs divided by 200 nano times area, which is 4 into 10 to the power minus 3. So this is 80 into 10 to the power minus 12 over 800 into 10 to the power minus 12. This is 0.1. 0.1 units, volts. How do you say volts? Why not electron volts? That can actually be both, depending, but no, see, this is coulombs and this is farads. Yeah, so it has to be volts. So this is 0.1 volts. So it just so happened that whatever the non-ideality was introduced by the difference in metal semiconductor work function was nullified by the positive trap charge in the oxide. We got lucky, essentially. That's what happened. In terms of threshold voltage, that these are still non-idealities. It's just that on the threshold voltage was not impacted. And how do we see it graphically? We know that the graph must shift in place of non-idealities to the left or to the right. This corner that you see where the depletion starts, or the flat band voltage is, where this starts to go down, this is exactly at 0. This can happen only when the non-idealities are somehow getting nullified, and they are getting nullified only when this term which you see V flat band is referred is 0. Whatever the non-ideality of metal semiconductor work function difference, that was nullified by the presence of trap charge in the oxide. Okay, so I'll just quickly solve this one last problem that we have. It says consider a MOS capacitor with the following parameters. So gate material is N plus polysilicon. Now instead of metal we are using a polysilicon, and a p-type substrate with doping is given as this. A gate oxide thickness is given and oxide charge is given. So this is a non-ideal thing. Okay, right. So and what happens to the threshold voltage of oxide charge increase 5 times. So this is the expression that we know. Okay, so we are required to find. So what we will do is that this term and this term will not change. The only thing we are changing is oxide charge. This will also not change. This will not change. The only thing that will change is this fellow. Okay, when you're increasing this oxide trap charge, I'm again assuming it's positive. Usually it's positive. That's what has been found experimentally. So if I increase the QI, right? So let's say when what's the QI? So yeah, QOX initial was given to us 10 to the power minus 10 coulomb per centimeter square, right? And now when QOX final is 5 times this, so it's 5 into 10 to the power minus 10 coulomb per centimeter square. All the things are remaining the same. So whatever VT1 that you are getting here, let's say you are getting some VT2 here, you can clearly see this negative term will be higher for VT2, correct? So VT2 will be less than VT1, or in other terms what we are seeing is that shift to the left. So let's draw it in terms of the CV diagrams. We have talked a lot of CV diagrams. So you have C, you have V. So I'm going to draw Yeah, let's say draw it with red, the original one. So let's say the original one comes out to be something like this. Okay, so this is the case 1. Case 2, it says the threshold voltage, so this is the VT1, let's say VT1. VT2 is less than VT1. Let's draw it here, green. Cox will remain the same, remember that. So Cox will remain the same, but there should be a negative shift in voltage. So this negative shift in voltage, everything else remains the same. This is your VT2, and this threshold voltage shift is coming due to the fact that we have more charge, more positive charge that is in the oxide. Or alternate way of seeing is that if you have a positive charge already in the oxide, that means you are effectively putting positive voltage on the gate. And if a p-type semiconductor is there, substrate, if you put a positive charge, then it's going to repel away the hole. So you already started a depletion, right? So you need to do much less work, and hence the threshold voltage shift is towards the negative side. Threshold voltage is essentially when you are achieving inversion. So you already, your positive charge in the gate, positive charge in the oxide has already depleted your semiconductor a bit. Hence you have to apply a much lesser voltage on the gate to invert it. That's the thing that we are doing here. All right. We are out of time for fixed oxide charges. VTH decreases. Yes. Okay. If it's a positive charge, yes, then it will decrease. Then it will definitely decrease. All right. So that's all from me. I'll stay back for a couple more minutes. If you have any doubts or comments, you may stay back. I'll share my YouTube link again, the channel link that is, and my email ID. So I'll upload this session soon, hopefully. You can refer to it, and thank you for staying. Thank you for your patience.